Cool. So I guess I can get started. As Susan said, I am Brendan from the Computer Science Department at Virginia Tech. I generally work on modeling interaction of users in XR, as well as looking at some of these privacy-enhancing methods. I will say this is a new community for me as far as IS&T, so I'm excited to hear what you guys think of some of the things I've been working on. So with that, we can get started. First things I like to show folks with this type of presentation is just an image of the eye and some of the things that I see in this image. A good example of this is the pupil of the eye. So that's the dark spot in the center. And what we know about this is that the pupil actually dilates as a result of emotional responses. So it could reveal personal interest, stress, cognitive load. I also see the eyelids, or specifically I could see the eyelids blink. And we know that blinking rate can reveal when someone is stressed out or they're lying to you. I could also see tears if they were present in this image. Now we don't know if it's happy crying or sad crying, but in theory we could see some emotions through that lens. We also see the iris region. So this is that band just outside the dark pupil in the center. And this is really important because this is actually a gold standard biometric for authentication. So we're actually seeing XR devices use this, from Microsoft to Magic Leap to Apple, for authentication and logging into your devices. We also see some information about the environment. So in this case, we see these little specular highlights that represent the lighting within the VR headset that's also being used for some of the tracking. And most importantly, we see what you look at, or what we call to as gaze in our eye tracking systems. So we know what direction you're looking, what you're paying attention to, and what you're thinking about, essentially. And our goal is to try to leverage this for our technology. So just to give you a little more insight into what eye tracking looks like, here's an example of a pair of glasses. Again, this is not an XR device, but you can see the form factor fits the AR wearable type of approach. The images that you're seeing on the right here, the sequence of videos, is actually us tracking the eye, or really tracking the pupil, and then projecting that forward to get a gaze direction and understand where on the stimuli or the medium that this person is looking and what they're paying attention to. So we have lots of examples of applications for that. I'll talk about a few for VR specifically, just as an introduction. So in this case, we can actually see somebody who's in a VR environment looking at a 360-degree image. So we see that floating green dot. That's actually their gaze position. You know, they wouldn't necessarily see their own gaze position, but we're visualizing this for you now. And it has lots of applications. In this case, we've thought about it for VR workforce training. So this is a real nuclear reactor on University of Florida's campus. And we designed this experience to get students into that before they've gone through their full year of certifications and training to actually go through a startup procedure. But we can think about how gaze data is useful. It shows where people are paying attention. Did they look at the right dial? Can we evaluate them while they're training? Things of this nature. But also for even prototyping future nuclear reactor designs, for example. So a lot of the other work I've done has actually been through some internships at Meta and kind of started a research line for interaction. So not just tracking that green position as it looks around, but tracking how you move your eyes while you perform tasks actually gives us a very useful signal. So if we track what we call the dynamics of gaze movements and interaction, we can actually use this data to predict when someone's going to select something. So you see someone playing a puzzle over here, but they're using a controller for the input. So if we're tracking the eyes during this, we can actually build models and try to predict those moments of interaction. And this is a very quick interaction task. The idea is, if we train these models and make these predictions in a very short-term window, we can make more naturalistic forms of input, whether that's gaze-only input, which you're seeing here on the lower right, or some sort of hybrid interaction system. So the Vision Pro, for example, is relying on gaze plus pinch for their main form of interaction. So that was just an introduction to some of the eye tracking applications. Really what I want to talk about today is that XR has a lot of potential to impact future of education, work, play, meetings, all of these things, but there really are two sides to every coin. So we also want to think about how we could mitigate future privacy risks from these XR sensors. So if you think back to that eye image I showed you, there was something relating to emotional response with the pupil, potentially what you pay attention to, and linking that to emotional response could be linked to your sexual orientation. But really, what's really important here is identity. The idea is if I have an eye tracking device on and enabled, I have no sense of anonymous browsing or no ability to have anonymous browsing. So the technologies I'll be talking about are how do we balance these XR applications and still enable them without leaking the identity of the users or people that are around the users. So I'll be talking about two main threats, one of them being more specific to eye tracking and the iris biometric, and the other being more about everyday wearable AR headsets. So my journey into the world of security and privacy actually started with the iris. So I collect a lot of eye tracking data. We would anonymize this by removing people's names and giving them a random number. But when I was looking through the folders of data, it was really clear who was who. And I decided just to test these things with an iris matching software, and well, it worked. We had enough pixel resolution compared to some of the standards, and could do fairly good tracking and matching with iris. This led us to develop a threat model that was more about how could somebody use this information to either identify you, right, if you want to be anonymous, or to, I guess, just steal your identity, right? If you can get access to some of these images, you could turn around and spoof and present that as somebody else and try to get into their system. So the threat that we're thinking about here is that your eye image could be leaking your iris pattern. We want to develop a technique that could still enable eye tracking in some of these applications without leaking the iris biometric out at the same time. So what we ended up doing is finding ways that we could actually manipulate this image in a meaningful way to make that balance happen. So one of the insights that we had here is that the features that we're actually using to support eye tracking and the features that support iris matching are separable in the frequency domain. So what I mean by this, I just kind of plotted those grayscale intensity values from line A to B. You see these kind of squiggly high frequency notes and features for the iris, drops down to the black pupil region. We see a nice Gaussian bump, low frequency for our corneal glint or from our lights, and then we come back up to the iris pattern. So if us being imaging science people, we can think about this as, oh, well, we can actually separate them. We could use something like a low pass filter and only let in the eye tracking features. And that's exactly what we did. So we determined that we could blur these types of images and have some impact on them. So let's say I have one example eye image here. Our blur parameter is sigma, so we were just playing with Gaussian blur initially, and this is just an untouched image. So of course we have some metrics. In this case, the gaze error from the eye tracker is about 1.4 visual degrees. Think your thumb at arm's length. Pretty accurate system. However, what we have is for the CRR, which is what I call the correct recognition rate, about 4 out of every 5 frames could be used to accurately do iris authentication on this user. So naturally, we want to look at this trade-off. If I crank that blur parameter a lot higher, we lose a lot of information. In fact, we can't even do eye tracking with a standard system because I can't find that pupil and track those regions. But we did get a lot of privacy because we can't actually recognize the iris anymore. So what we're finding is there's always some sort of trade-off. So in the middle, if we adjust that blur parameter, we can start to get eye tracking data again, add a little bit of error to it, but we drastically reduce that correct recognition rate to only being a few frames leaking the person's identity in this initial system. Another insight that we had is beyond just software blurring, we can actually think of the ways that users can control this through hardware. So this is a more traditional pair of eye tracking glasses, so not an actual XR headset, but as long as you have some way to adjust the camera focus or distance in this case, we can think about how we can add blur through hardware. So in this instance, we just bring it out of focus by increasing the distance, and we can get the benefits we're looking for while still enabling eye tracking. So we can do this in software and in hardware. I don't want to go too deep into a lot of the technical stuff here, but obviously the intuition is that there's a trade-off. The more blur, the more it affects utility. So we measured this with some eye tracking experiments, and this was some of the very initial work. And depending on what you're doing, so if you're just viewing some targets on the screen, we can see this green dot jump around, and in these secure, defocused configurations, we still get reasonable eye tracking data. So this was just a very simple demo, and they looked at some targets on screen. That's great. But what about actual applications, right? Who cares if it's about 2 degrees off? You know, what are you actually using this data for? So we had extended this work in the context of social VR. So we have our bald friend here on the right, not as cool as some of Koki's avatars, but what we wanted to do is say, okay, we have this pipeline from eye image to gaze data to mapping it to a virtual avatar. If we're adding that image blur at the early level of the sensor, how does this affect things downstream? So we did this. We simulated some experiments. We had people interact with this virtual avatar and had them rate their perceptions of the interaction. And as we expect, as we go from left to right on these little figures here, we actually degrade some of these social qualities. So high on this plot, 5 is the highest quality, 1 is the lowest quality. And as we increase that blur, we start to see the perceptions of this interaction also degrade. So what we're seeing is that there is an actual trade-off at the application level for these types of approaches as well. If, say, you do want to go to some sort of virtual chat room in an anonymous way, or some other applications you could think of. So to summarize kind of the iris part of this talk, because it's about my halfway point, I want to switch over to the AR bystander work. We can actually transform the eye image. We can turn off the iris biometric. We can do this using blur. We can do this in software or hardware. And hardware is nice if we don't trust the manufacturer, the platform, or the arcade or the public use case that we're going for. And the last takeaway that's really important is we want to select these parameters based on the security utility trade-off. which really depends on the application we're going for, as well as the threat models that are attacking us. A very accurate iris detection model might be really hard to beat, for example. So I wanted to step over from that iris and eye tracking talk to kind of more bystander privacy in AR. So in this case, I'm not looking at the identity of the user, but actually the identity of other people. So as Ben said very early on, we're going to start wearing these devices around and want to think about privacy from this context. So shifting away to this, we can think about a lot of different headset applications. This could be medical, so they assist people during a triage, and they can quickly pull up patient information, for example. However, if someone's using this system for that, they might actually be capturing other information around them. And our specific threat model for this work, and we can talk a bit about threat models if people have questions later, is that the user is not really aware that they are leaking this information. It could be some third-party app that they just downloaded. It could be helping them translate text or some other assistive technologies. This third-party app has a reason to ask for visual data, but could actually be using that visual data for other applications because these bystanders are present in the field of view. And we really focused on facial recognition, because I had mentioned identity is extremely important, as it's kind of a first order risk for this type of privacy concerns that we're having. So thinking about this, we actually end up proposing a way or an API to process this data that actually sits between the sensor and third-party applications that ask for the sensor data. To give you a little bit more insight into what that means from a threat model, and I don't want to get too technical here, of course, is that we're trying to remove bystanders from sensor feeds. The idea is that models can easily profile or identify these bystanders. For example, you take this image. Of course, the images are actually blurred to protect our participants, but imagine that these things were completely open. You could run something like deepface on them and say, oh, it is a person with a certain ethnicity, a certain gender, a certain emotion, things of this nature. What we're proposing is a privacy-preserving API that, again, sits between the sensor and the third-party apps and sanitizes the data before passing it on. So by doing this, we could turn off the ability to use something like deepface for inference and turn off these readings if we can take those pixels away from the sensor data. So what this ended up creating was actually the technical task of identifying who in the camera feed is a bystander and who is the subject of conversation. So we can see some red blocks here for random people, as well as somebody who is front and center for having a conversation. Now, this isn't a new computer vision problem, but making it work effectively in real time is a novel problem from a systems perspective. And again, we could always just blur out every single face or black out the pixels for every single face, but we see these applications that actually support users, whether it's someone with Alzheimer's who needs memory support, autism who needs help reading expressions, or other social behavioral interfaces. And the way we've really built this system is to say, hey, we have conversations with people every day. We aren't really paying attention to every single other person we walk by. Could we use social interaction as kind of an implicit consent to start recording or processing this data at a sensor level? Now, if we think about this problem, there's of course the naive approach of just detecting faces every single frame that comes into the device and blank out all the faces that are bystanders. The problem with this is it actually produces a pretty low frame rate on these mobile head-worn AR devices that we think about. So at this time, we were working with the HoloLens 2 because that was a pretty standard device, though we've been trying to play with the Magic Leap 2 as these things have been coming out. Either way, we get a very low frame rate if we try to do this every single frame. Now, the system that we're proposing and patented and published out here was actually called Bystand AR, off the name. And we start by trying to actually detect faces at interval to balance performance. So I don't need to actually detect faces and do this blocking and detection every single frame, but do this at some arbitrary interval just to balance this power. Now, the cool part about XR is that we actually have some 3D understanding as well. So let's say I detect a face and I know where it is relative to the user. If I take a step to my left, my device knows in 3D coordinates how I'm moving relative to that box. So assuming the person isn't sprinting by as fast as possible within a certain frame rate, we can actually still make use of this detection at an arbitrary interval and still get away with blacking out these faces while the person moves around and does some other forms of interaction. So we leverage that 3D understanding in this context. So now we know how to black out the bystanders, but now how do we actually know who the subject of conversation is? So as I had mentioned, we're thinking about social context and cues as this type of implicit consent. I'd mentioned eye tracking data before, of course. In this case, we actually leverage the eye gaze and the voice during this conversation. So I'm looking at you and speaking at the same time for a sustained period. That flips the switch from being a bystander to a subject of our conversation. Then we can track this over time across the various faces, even though the faces are blacked out at the pixel level. So we're using these social implicit cues and making a determination for each face, bystander, or subject. So of course we wanted to evaluate this system, and it was a very novel system. So what I didn't show here is that we pass this data off to the third party based on, of course, the bystander subject piece there. What I also didn't show is that we can actually do this for the depth data as well. So even though the depth sensors aren't quite good enough on the HoloLens to do identification itself, we can imagine that these sensors might get better. There might be thermal sensors. All these things could be possible in the future. So we had some metrics that we proposed. We know we want to balance privacy and utility. So a good metric for privacy is how many bystander faces get through for each frame across this whole data set. Likewise, for data utility, we can think about how available the subjects are. So do we actually have the subject face available when we want it to be? So again, I won't super dive into the numbers here, but technically it kind of works. We tested two different thresholds, two different levels of gaze and eye voice combination. So how long do I have to make contact with somebody and speak to them before the system will unlock their face for the APIs to access? And of course, we've had some different results. Overall, everything was in the pretty high 90s, which is really good for bystander privacy, right? We're above 99% with one of our thresholds. We are around 98% for the other one. So we're seeing these types of trade-offs as we analyze them. So this makes sense. Again, we have a trade-off between privacy and utility, depending on what our goals are and our priorities. Another important part about this is that it's actually a real-time system that we're talking about. So I don't want to dive into the super nitty-gritty details, but we wanted to see, if I'm actually adding the system, adding some extra technology and processing, what impact does this have on the HoloLens that we worked with? So we ended up just doing face detections every 8 frames for our system, which was pretty reasonable for performance. We did drop our frame rate from 52 about to 34 frames per second. The main reason for this, though, is we were actually using Unity 3D, so some third-party game engine as an API to implement and test our system, that we know would be much better if we embedded this within the operating system and integrated this at the platform level. We looked at some of the memory and power impact there. So an extra 15 minutes being lopped off your battery life is one of the impacts, as well as a little bit more memory usage and CPU usage. So it all depends on what you're using the applications and headset for, but there are some trade-offs there that we're observing. I won't dive too deep into this just because I'm starting to run a little bit out of time, but we did do a perception study with the bystanders from our study. So we would show them frames from the actual study, again, blurred just for your purposes, but they would see their original frame, ask them how comfortable they feel. We start to show them what a deep face or deep fake model would do with this information, what we could infer from it. And then they started to get a little bit more uncomfortable. We see the red, the orange, and the yellow increase. And then we, of course, show them what the output from bystand AR would look like. We started to see that people did actually feel more comfortable being present around these devices as a result. So high-level takeaways, for the context of AR bystanders, we can build a privacy-preserving API that targets obscuring bystander faces that is feasible for head-worn, everyday AR devices and can run in real time, or near real time at least. And the main takeaways that I want you to take away from this talk, and I'm really interested to hear your questions, is that we should be considering privacy mechanisms for identifying sensor data, whether that's your face or the user themselves and their iris, things of that nature, and that we can actually pull this off, right? We have sensing approaches and want to think about privacy-preserving sensing at the sensor level instead of just offline data sets or analysis after the fact. We can build these into real-time applications. I'm really interested to see what other sensors and devices people come up with in the future. And one note before I wrap up in terms of critical future directions, what I'm really interested in is the privacy of the sensed environment itself. There's this really nice paper I used Nick Security. I was actually just looking at home scans from Zillow, like the Realty website. And they actually did a really interesting analysis on personally identifiable information, things that could be used for targeting of ads or targeting individual people or populations that were present in this data set. So we can also think about sensing the environment and not just bystanders, and how maybe we could protect that as we build 3D SLAM models and all the other things that support XR. I think this is completely present when we think about point clouds. So this is actually some pretty old work. I'm sure they've improved on it since. But if I take this point cloud that you have on the left-hand side of the figure there, I can actually reconstruct what we're seeing in the middle as a reconstruction, the real environment. So even if it's like, oh, well, our point cloud is pretty sparse and we reduce the resolution, these AI and ML techniques can actually reconstruct these things very well. So you can see a bookshelf, you can see painting, you can see the structure of the home. All of these things could be, inversely revealed by sparse point clouds. So this is something we have to think about. My acknowledgements, quick. During my PhD, I was supported by NSF, Google PhD Fellowship, internship with Meta. Meta supports me now with some funding as well as the American Indian Science and Engineering Society. During my time at VT, I've been supported by state-level programs and agencies, our Center for Human-Computer Interaction, as well as our Institute for Creative Arts and Technology. So with that, I wanted to wrap up and take some questions if you guys have any questions. Thank you for your time.